So this summer, I was an intern at Red Hat, and I worked on probabilistically analyzing worst-case execution times on real-time system. Now, I know that sounds like a mouthful, really scary, but I will break it all down. I am assuming no prior knowledge. That's wrong, my title. Let's fix that. Yes, I was offered full-time at Red Hat. I'm working full-time at Red Hat now, so yay. So what are real-time systems? Well, first of all, what are normal systems, non-real-time? Well, in non-real-time systems, correctness is, well, producing the correct answer every time. In real-time system, we append that definition and say correctness is also producing the correct result within a bounded time, always, right? And therefore, when analyzing performance in real-time systems, we only care about the worst case execution time. And I don't know what happened to that video over there, but yeah. Now, applications of real-time systems include airbag controller, for example, flight controllers, pacemaker. And what this video would have been, if I don't know what happened there, it was essentially, if your airbag doesn't open at the correct time, then it's useless to you. And that's an example of a real-time system. Now, the entire real-time system thing really comes down to the worst case execution time, finding what's the worst case scenario, because that's what you want to plan for. And that's a challenge in real-time systems. And traditionally, this was found using static analysis, like painstakingly figuring out worst case for my hardware, for my operating system, for the specific software I'm running. And it was very complicated, often involving specialized real-time operating systems on specialized hardware. But at Red Hat, we make Linux, and Linux is a general purpose operating system. Now, we have made progress towards making Linux behave like a real-time operating system, but at the end of the day, it's not a real-time operating system, and it's way too complex for static analysis. Think, and the hardware too, because this is designed to run on commercial off-the-shelf hardware. Like, if you're familiar with these terms, think speculative execution, branch predictors, caching, and various kernel housekeeping. So, how Red Hat engineers then approach this, that, okay, we observed that if you run our measurement tools for a while, right, and extract the worst latency measurement we get, usually after a while, it doesn't get much worse. And maybe surprisingly, this actually worked surprisingly well, usually, but you know, usually it's not good enough for real-time systems. And we have other problems too, like what does a while mean, right? If it's too long, well, you wasted a lot of compute and a lot of money. If you did it too short, well, you have broken software because this is real time and time-boundedness matters, right? So we can do better, and that's where I come in. Essentially, we needed a more methodical way to find worst-case execution bounds with measurements because static analysis was, you know, not feasible. And this is where extreme value theory also comes in. Now, extreme value theory is the study of statistical extremes. It's essentially analogous to the Central Limit Theorem, if you're familiar with it, right? You take a bunch of samples, take the mean. If you plot the means in a graph, you get a normal distribution. Same deal here, but now we are working with maximas. And it's equally, actually, it's more powerful because I'll explain why it's more powerful, but like the Central Limit Theorem, it is non-parametric. It doesn't assume an underlying distribution. And there are essentially two different independent formulations of it, which I'll get to. First, I want to talk more about the point about why I say it's more powerful than the Central Limit Theorem, right? Yeah, now you see a bunch of like graphs here, right? A bunch of different peaks. This violates all of the assumptions of independent, identically distributed, but it's more, since you only care about the extremes, actually it turns out if you trim the data to just those extremes, that data actually behaves independent, identically, which is why I say that EVT is more powerful because, you know, in the real world, you have real world stuff happening, you know, like on hardware, shared resources, cold caches, you know, forget IID, that's not happening, right? Now, I'm going to focus more on this formulation of extreme value theory, which talks about you basically collect a bunch of measurements, you take a threshold and you plot them, and actually assuming the assumptions hold, it leads to something called the generalized Pareto distribution. I'm not sure if I pronounced that right, but yeah. And this threshold is not arbitrary, but how that's selected is outside the scope of this presentation. But the TLDR is there's something called the stability graph, and that tells you where plausible thresholds might be. So I'm going to go get straight into the demo / results. So let me remind you, before we just ran stuff for a while, picked the worst latency, and hoped it worked. Now you run it for a short time, maybe 1 hour, look at it, collect more data, look at it, and essentially you see that as I'm adding more data, is my answer converging to the same answer? And you wait after, like over here, you still have unexplained outliers. So that means you should keep collecting more data. You keep collecting more data until your distribution parameters converge, and you no longer have to change your thresholds. Essentially, adding more data doesn't change your distribution much. So over here, at this point, after 96 hours of data collection, we see distribution parameters are barely changing, and you barely have to re-threshold, right? And this is better. Now we can answer the question of how long should I run my test for, and you don't have to waste compute by arbitrarily just picking the worst case. And now, because you can mathematically model the latency distribution, you can actually use that model to extrapolate data for much further than however long you did your test. So over here, I ran the test for 96 hours. Well, given that our assumptions hold, which they probably do for this, as you saw, it was a pretty good fit, we can actually extrapolate this. And what this graph over here is saying is, for example, if you run this test, our model is saying if you run this test for 1 million years, then after 1 million years, we can say with a 99.9% confidence interval, based on our data, that our worst case latencies won't exceed 15 microseconds. Now that's very powerful, because you don't have to run your data for 1 million years to find what the worst case will be. Again, assuming our assumptions hold, which they probably do for that. Yeah. So essentially, these were the results. Obviously, a lot more went into making sure those assumptions were met. There were issues in the systems, as I briefly mentioned, issues with cache, issues with background kernel housekeeping tasks that had to be addressed first before this methodology could be applied. But eventually, I made it work, and there it is. Any questions?